For the last talk of the morning session, we have the pleasure of listening to Mihaela Pricop-jeckstadt from Dresden, and she will speak us. She will tell us about spatial learning to machine learning, an unsupervised approach with applications to behavioral science. Thank you.
So first of all, I want to thank the organizer for inviting me here. So this is kind of work that I started 6 months ago together with Alexander Garte from DCNE in Dresden. This is a center for studying neurodegenerative diseases. And I think it fits into this framework because we talk all the time about learning, so machine learning, deep learning, unsupervised learning, but I think it's interesting to look exactly what is learning and how is brain doing this, and what are experiments and what are results regarding learning in the brain and not only learning in mathematics. And so the first part of my talk will present some design of experiments that allow neuroscientists to draw conclusion about the learning process in the brain. This is a very interesting topic nowadays, since we are living in an aging society, and loss of memory and loss of learning capacity is getting a huge problem for so in personal level, but also for the medical system. And after that, I will try to show how this kind of experiments can be used not only to test for the impairment, for disabilities in learning, but also for testing for the best, due by an example from jet pilots, so a data set from Bundeswehr. And in the end, getting from spatial learning, we can get to very interesting mathematical questions in machine learning. And so I will try to develop some ideas about some sparse model-based clustering that can be used in this setting, and also some ideas about how this can be also developed in the future. So the first part of the talk will be about this design of experiments and about about memory and learning. So memory is a process of storing and retrieving information in the brain, and long-term memory is very important for in neurodegenerative diseases, because loss of long-term memory is one of the first symptoms in diseases like Parkinson, Alzheimer, or in general dementia. So this long-term memory can store a very large quantity of information, can maintain that information for a long time, and this information can be about facts, events, perceptual skills, spatial models, attitudes, beliefs about ourselves and others. So there are different type of things that we are actually retaining in our memory. And the processes that they are involved in this are registration, meaning transferring information into a form that can be retained; retention, this is the storage and information; and remembering. This is the retrieval of information, and this is what we are going what scientists are focusing on, and for which they develop different type of experiments. Now, remembering itself has also some sub-processes. So it's the recollection, the reconstruction of events or facts on the basis of partial cues; recall, the active and unaided remembering of something from the past; recognition, the ability to identify previously encountered information as familiar; and relearning, the ability to learn once familiar material more easily than unfamiliar material. So there is a challenge to design these experiments, to not only to try to assess the memory loss, but also each of these sub-processes of the memory. And one type of memory that it's and of learning that it's really very fast impaired in Alzheimer, for example, it's the spatial memory, and this spatial memory is localized in hippocampus. So hippocampus, this time worked. So hippocampus is part of the brain inside the temporal lobe, and it's responsible in general for long-term memory and for spatial memory, navigation, and this requires reference memories that is necessary to remember information that remains constant over time. So this is called task-specific information. The way people actually remember is through a cognitive map, a neuronal representation of the layout of the environment. So this is a theory which is called cognitive theory in neuroscience, and it looks like inside of hippocampus this kind of cognitive maps can be actually developed. Now, what is the evidence that actually hippocampus, that this spatial memory, this spatial learning is focused in hippocampus, where again it's about how you can design an experiment to test this, and one of this kind of experiment was proposed in 2006 by McGuire, Ulit and Spires, and they consider MRIs of a hippocampus area in the London cab drivers compared to the general population, so case control design. And they discovered that actually this right hippocampus area of London cab drivers is larger than the mean of the population. And this is possible because of the phenomenon called neurogenesis. So when we were in school, we learned actually that the neurons don't multiply. So we are born with these neurons, and they die with the time. But actually, in the last 20 years, neuroscientists discovered that there is neurogenesis, and one of the areas where this is possible is in hippocampus, meaning that if you are learning like cab drivers in London streets, so you need to learn how to navigate through the labyrinth in London, then you are actually using your hippocampus area very often, and then this produces cells, and this area becomes larger. So this was one evidence about that. And now, since spatial learning is so important in detecting early Alzheimer disease, scientists focused on developing this kind of tests for for testing the spatial learning capabilities. And one of this is called Morris Water Maze experiment. So in this experiment, a rat here is placed in a small swimming pool, and in which the water is clouded with powdered milk such that it cannot see, and a hidden platform is located just under the water here, and the rat's goal is to learn the location of this platform. Now, from trial to trial, the starting location of the pool is varied, and the animal must learn the location of the platform on the basis of the cues on the room, so visual cues in this case, testing recollection and recognition. So these are the two processes in the brain that we talked before. Now, in the first trials, the mice the rats in this case, the rats look like to find this platform after longer time and after a longer path, and with the time they improve. So this is an indirect sign of spatial learning, and spatial learning with the help of the cues. So interpretation rat appears to be encoding spatial relationships between the hidden platform here and the visual cues. Now, the initial experiment in 1981 done by Morris actually did not include the cues. So he is actually testing recall, meaning that the rats could find this platform even without any visual, auditory, olfactive cues. And this kind of experiment is has another challenge now. So from all this, what is actually the task to be, what is a feature, like in machine learning, that needs to be considered as associated with spatial learning. So there are a lot of possibilities. I just give you some of them. So they are related to the time that the rats need to take into this labyrinth, the distance they are using, and also of the directional changes they are making. So you have escape latency. This is usually the first sign, the first variable that's taken. It's considered to be more relevant, and is the time it takes to find the platform confounded by swimming speed. Then you have the distance, so it's the path length needed to reach the platform. You have initial heading error, it's the deviation from the optimal path. Floating time, it's time spent to sink, so without swimming, without moving. Then number of directional changes, preferred direction, it's the mode between the chosen direction. Distance, so is this endpoint to G, so distance between the guess point and the real one, so the distance between the endpoint and the guess point. And goal crossing is a measure of adherence, how often mouse actually intercourse in this treasure in this platform area. Why do you need more features to establish this learning quality? Because there are a lot of confounders. So you can have differences due to gender. You can have differences due to what's called sigmotaxis, the tendency of animals to stay close to the walls of the pool. You can have differences in learning due to a tendency of the mice to float passively in the water until rescued by the experimenter. This actually shows more the motivation of the rat or mice, and then the actually learning quality in the brain. And it depends also on the type of the animal. So if it's a rat or it's a mouse, because they do also have special behavior and special, for example, rats like to swim in cold water, and so there are differences in their behavior. So it is not really so evident how can you use these variables to draw conclusion even only about this quality of the spatial learning. Now, it is interesting to use this for mice and it's for rats, but our idea is to use it for people. So in general, the neuroscience is now focusing on human diseases, and that's why this water maze experiment was transferred now to humans, and this was done with the help of computerized 3D graphics. Now, participants were placed in a virtual circular pool in a room with distal cues, and participants were told to escape from the water as quickly as possible and using a joystick to navigate to a platform hidden under the surface of the water. And again, as in the mice, in the Morris water maze experiment, participants started from different locations more times, and the number of total trials depending on the session type, which we talk about later. So just to get an idea how this can be, this is something that you can do it at home. This experiment with virtual water maze, the scientists from UCL and the University of East England developed a game called Sea Hero Quest, Navigating Dementia, where you can actually test your navigation and spatial spatial learning qualities So it looks like this. And I think that it might be nice if people try it, because during this game, scientists also are gaining information. So you are sending your data, some information about yourself, the results of your testing, and as you see, this is a generalization, I would call it, of a Morris water maze experiment, but they also can look at more detailed reaction like eye movement, and you can do it, it's for free, so it might be interesting to look at that. And and it might be even fun, I think. At least I thought that it can be really nice. They have a very nice motivation, something like this. Okay, so you can try it and see if you actually qualify for the best or not so much in this spatial learning. And not only, as you see, they actually developed other tests that might test other reflexes and other type of learning, depending on cues, no cues, searching, or just remembering. Now, in our case, we went for something more practical. So the idea is to use this data from, so this experiment from virtual water maze to discover new subgroups or to discover new partitions in candidates for pilots. So Bundeswehr has so German army has a problem. They do not have so many young people who are interested in flying, and it's also the problem is that they cannot afford to take so many candidates because it's very expensive to have this kind of education, and so they are testing very hard people who are candidates for who want to become pilots, and they have a very good rate actually of success, meaning that something like 95, between 95-97% of the pilot candidates actually they do finish their education. Their problem is that they have too much false positives, as they reject too many people, and they would like to have something like subgroups that can be considered for this education. And the idea would be to see if this virtual water maze in different situations, maybe in a transformed form as we saw before, can be used to do this. And to this aim, we had a small study with 59 pilot candidates aged 17 to 36, and they actually so they followed the virtual maze session, actually more pre-test session. The first trial where the reflexes and the motivation were tested, then a training session, it's called acquisition, where we have 9 trials, and this was testing recollection, and a retention test called guess session, and where we have 6 trials, and we're testing recognition after, so this is made after approximately 24 hours. And it was done with no platform, meaning that just people were just looking for a treasure and we were just counting the time or the crossings around the area where the treasure was before. So our research questions are, first, are the learning variables associated with the flying ability? So can we actually use this experiment to improve the classification for pilots or for pilot candidates? And the second, if so, could the learning variables identify new subgroups in the candidates corresponding to new flying fitting profiles? So for the first question, we have already an answer. So we had, except for the learning variables that we saw before, those like latency and distance and so on and so forth, in all these, in the 3 sessions, we have also the normal psychological and navigational tests for pilots. So we have 55 ability variables, and they are variables that they are measuring physical skills and reflexes, like MIC, sensomotorics test for speed, for stick usement. So these are also tests that are repeated 3 times, visual and psychomotoric tests. We have cognitive tests that they are testing logical thinking, verbal analysis, quantitative reasoning, computational tests, decision making tests, and also tests about job motivation, performance commitment. These are, some of them are tests, some they are also based on some interviews. So we have 55 variables here, and the research question is, are the learning variables reflecting flying abilities? We went for an explorative approach, so what I call the 2-step method. So in the first step, we identify cluster of candidates based on learning variables. So we have univariate learning variable in the pre-test session, and longitudinal learning variables in the session of acquisition and guess. And so this can be done unsupervised by clustering, and then in step 2, we test association between these subgroups with ability variables, and this means that for the subgroups identified in step 1, we just simply apply the Mann-Whitney or Kruskal-Wallis test to see if the means, so it's a they are non-parametrical test, and test if there is a difference between the means of abilities variables in between the groups. So the first step was about clustering, and to do this we needed to look at what kind of longitudinal clustering methods exist nowadays. And there are some that like k-means longitudinal, so they are generalizing k-means algorithm to longitudinal data, or k-means longitudinal based on Frechet distance, KML shape, which actually considers the distance, so the Frechet distance between the time, so between the time dynamics curves, like in here. So this would be something like times, and you just have the distance between these curves. or long clusters. This is model-based longitudinal clustering. And since time dynamics of the learning variables contains information about memory and also about learning and about motivation and so on, we found it interesting to use this KML shape. And after doing this, we went the normal way. We have different multiple starting points, clustering with lowest internal compactness as a criterion for the number of clusters that should be chosen. In this case, Kalinski-Harabat's criteria. And so this would be the first step. And in the end, we get, for example, in this ability test that we have seven clusters, and as we see, the behavior was pretty much very hard to interpret, but we still can see. So what we are interested to see would be like the ideal case would be if we have here the distance. In the first trial we have large distance, and then in the second trial the people needed less distance to get to the treasure, and so on and so forth. So this would be a rational, what I would call the ideal case, but this would also reflect perfectly this learning aspect, but it's not always the same, first due to the obvious learning process that it has some randomness in itself, but also due to the fact that other factors are also involved, like motivation. And so this is a very big problem, like people who, for example, can get here from very low distance, meaning that they find the treasure in the first step, so first, second, third, and after that they are not interested in anymore, they are bored, and so then they actually find the platform after much longer time or much longer distance. So this is something, but this is not good if you study only the spatial learning capacity, but it is good if you are looking at pilots, because actually you are also interested in people that can focus, can concentrate. And so in this case, this kind of clustering method that also show this phenomenon were appropriate for this method. And in the end, after we, like in this case, we detected these 7 clusters, we just compared these cognitive tests for a bit normal cognitive tests for pilots, and see if there were statistical significant differences between the means in these clusters. And this is what we got, meaning that in the acquisition session was a session that actually was the training session, so it's the learning, we were testing the learning process there, and here were the variables that we were used for partition. You have distance, so the distance that the people use to get to the treasure, floating, the time that they spend thinking, latency is the time that they spend to get to this treasure, and this initial heading error, so it's the distance between the perfect path and the path they taken. And as expected, we can see here that this cluster detected based on this variables in the training experiment, they are very much differentiating here, so that they are actually reflecting some powers of judgment, so in general cognitive qualities, so cognitive processing capacity, quantitative reasoning, and so on and so forth, but also some skills like this MIC that they are, or sensomotoric tests that they test speed and speed. Now, the first session, I mean the last session actually, the guest session is the session that's taken after without the treasure, meaning that the people just they don't find the treasure anymore, but they need to assess where it was. And in this case, yeah, the conclusions are not so clear. In any case, it looks like motivation for looking it's very important. So there are really groups of persons here in the guest session that they lose their motivation very easily, and there are some that they are highly motivated and they are still looking even if they can't find the platform. So people were not told that the platform treasure is not there anymore, so they need to have some endurance to look for that, and it looks like this is also reflected in the variables here. So after we answered this question, it looks like really these learning variables are associated with flying abilities or some cognitive qualities that are necessary to fly. Now we would like to see how can we actually discover new subgroups into this, and so into the set of candidates. And to do this, of course, we want to do this unsupervised, and we are looking for some algorithms that they allowed to use multivariate clustering based on correlated variables, because our variables are correlated in more than one direction, so they are correlated as cognitive functions, cognitive variables, but also they are correlated as repeated measurements. And also they have kind of a unbalanced design, meaning that we have variables that they are they have a different number of repeated measurements. So some of them are like we saw before, 7 times repeated. So each trial showing the improvement in the learning, or some of them are only 3 times, and some of them are even univariate. So we consider a data point yj to be this vector that it actually contains all the variables, and we ordered, this makes no difference, this variable such that we have a decreasing order of the trial number. Now the total number so the total dimension of this vector would be something like an L, depending on P and on this number of repeated measurements. And our idea would be now to go for a model type clustering, and to use the whole information that we have. So before we actually splitted the information, and we went only for each variable, and we see if correlates or is associated with each of the other variable in the ability class. But in this case we would want to see clustering and using the whole information, see what's happening if we get some interesting subgroups. And to do this, well, this is hard enough if you have only repeated measurements like we saw before, using this longitudinal clustering. Now we want to consider also this correlation, and we went for simplification of this covariance model using separable covariance model, and using a low number of parameters for the covariance. Of course, this is now the way people attack this kind of problem. So using the Kronecker product, so we are going to consider as an assumption separability between time dynamics and association pattern. So this kind of cognitive functions, usually in multivariate clustering, it was assumed a kind of independence, local independence of these variables, and this given the information about which partitions they belong to, but we can't do this, and that's why we consider, we model the unobserved heterogeneity with the covariance matrix sigma j, and depending on a p star parameter that on a dimension much smaller than p, and modeling correlated temporal data with covariance matrices omega g, and depending on p star parameters. And the whole vector yj actually will have this kind of a Kronecker product covariance matrix as proposed here in Andalucci and Villoli in 2015. Now, this approach has clear advantages. First, it allows to model directly the time or trial dependencies, and second, it allows to have a more parsimonious model and to reduce the number of parameters. And of course, if you take here omega j or sigma j to be the identity or kind of a diagonal matrix, then you get the previous models based on independence. Now, the second problem would be the unbalanced design, meaning that you have different trial numbers, Tj, and we need also to simplify in some way, so we have the assumption that the same trial covariance structure is valid for each variable, and we consider the partial permutation matrix here, which reflects the trials, the number of trials, and each trial, one, the first, the second, and so on, for through the set of rows. And then we can really write the covariance matrix as a product between this partial permutation matrix, the Kronecker product, and the transpose of the partial permutation matrix. Now, the model that was chosen was Gaussian model-based clustering, and we were working here, we are trying to identify this G multivariate normal distribution from our data, incomplete data Yj, and we have a parameter space where we have this mixture, mixture weights, we have the means and the parameters corresponding to the two variances, covariance matrices, and of course we could look, we should first look which kind of covariance matrices, which kind of models we are able to consider in this case. So we have here normally a lot of constraints, especially regarding the PG and the matrices or sigma g and omega g. So to do this, we were looking to possible models that they are unconstrained. The first one would be like in or constraints that they are easy to deal with, and so unfortunately for the ability covariance matrix, we still look only at a kind of pattern covariance structures like spherical with and without varying volume, and with unit volume, meaning also identity with kind of one parameter or maximum g parameters. And of course it might be possible maybe in the future to look also at general kind of eigenvalues decomposition here, and this type of relation between the eigenvalues would give us again the geometric feature of the clusters, like shape, volume, orientation. So if you have one large eigenvalue, then you would have something like a hyperplane. If you have two large and eigenvalues, then you have a then you have a hyperplane. You have a line in the first case, and or if you have almost equal eigenvalues, you can get something like spheroid form. But in this case, we just consider, we made this easy, and for the beginning at least. And for the time covariance matrix, there is a nice model that actually contains 8 submodels proposed by Nicholas and Murphy based on this linear regression autoregressive model, and this allows, so due to a modified Cholesky decomposition, you can have this diagonal matrix with strictly positive entries, and this has a nice interpretation in this regression regression model, so prediction model for as innovation variances or the variance of the prediction error, and the psi j is a unique Lau triangular matrix with diagonal element 1. And this has a nice, also nice interpretation as the coefficients of this linear model. And so, if we take this kind of models, we can avoid the constraint maze of the constraints there, and we have also a number of parameters that are feasible. So, between t minus 1 over 2 plus 1 and gt minus 1 over 2 plus gt. So in general they do not depend on p, and we cannot, we don't want to depend on n also. Now coming to the method itself, we know that the maximum likelihood estimator in for mixture problems is very hard to determine, is sometimes does not even exist due to the so singularities points on the bound of the parameter space, and there are problems with identifiability and with local maxima. So if you have points, sample points that they are close to each other, then you can get easy into local maxima there, and there is hard to discriminate between clusters with the same mean and different covariances. So there were some approaches in the literature about this. So you have first approaches about local estimates, then restrained parameter space, constraint maximization, meaning you need to go away from the this problem of the exploding variance going to 0 on the border of the parameter space. So there are some constraints on the on this sigma and on the variance, and there is also an approach about penalized maximum likelihood. And in general, there are also some approaches with penalization and model this kind of model-based clustering. So an AM algorithm for for lasso and Gaussian mixture was first proposed by Pan and Shen in 2007, where they consider heterogeneous independent univariate variables. Then Sun and Wang in 2012, they consider group lasso and Gaussian mixture, again heterogeneous independent univariate variables. And in both cases there were some numerical introduction of the AM algorithm for this this kind of models, and some numerical considerations. And there is also the approach of lasso penalized Bayesian information criterion for mixture of factors analysis by Bhattacharya and McNicholas in 2014. We try to look at classical lasso, so we consider here this penalization term as a classical lasso. The penalization is on this mean of the as the parameter, one of the parameter of in the parameter vector, and we went for a restricted parameter space idea. In this case, first you have kind of a boundness, and it's a boundness condition on the parameter space, and also on the logarithm of the pj of the mixture probability mixture weights. And we fix the number of clusters, and we consider the number of the variables p and the true parameter phi 0 depending on the number of observations. Now, if what is the problem here? Of course, we have it's non-convex function, a non-convex and loss function. If we consider the minimization of all these parameters, and so the idea was, and it was not mine, was actually from Scheldorfer, Bühlmann, and van der Geer, was to try to bound this score function of the log likelihood with the process that is smooth. So in this case, with supplementary conditions on the eigenvalues of the covariance function, covariance matrices, we get something like L2 norm or Euclidean norm of the vector yg and square of the Euclidean norm. And this can be done by computation based on again extra conditions on more restriction on the parameter space. Then following also something like similar from Stedler, Bühlmann, and van der Geer in 2012, you can actually look at the empirical process defined here, Vn phi, and you can actually bound it. It's Lipschitz behavior here with respect to the parameters on a large on a set with large probability, and these probabilities depending on this G1 of the process, the smooth process, the smooth that we defined before. And this can be done relatively easy. I mean, as I said, the idea comes from Stedler, Bühlmann, van der Geer. Just generalize it to a mixture of chi-square random variables, and then use the same arguments as in Scheldorfer, Bühlmann, and van der Geer, based on the entropy and the supremum of the stochastic processes to get this kind of concentration inequality for our empirical sum. And in the end, using all this kind of concentration inequality, you can obtain a asymptotic consistency argument result on the average excess risk here. So practically, the excess risk is the Kullback-Leibler distance between the two probabilities distribution, and in this case, this is the empirical Kullback-Leibler distance, and this can be seen to converge to 0 in probability. So on a set of large probability, as we saw before, for some again some more boundedness condition on the eigen values of the covariance matrix, and for some sparsity condition on the sorry, here it should have been mu0, not phi 0 for the mean. And so this would be the interpretation of this would be if we have here if our phi 0, the exact parameter, has also the property that the Fisher information in phi 0 is strictly positive definite, and you have a third derivative that's bounded here, then you have this average excess risk can bound the Euclidean distance between the two parameters, meaning that actually the distance between the parameters phi and phi 0 is going to 0 when on a set with large probability. Now, how can you reach this? I mean, this is nice to have kind of a consistency result, but how can you reach the minimum of this function? We thought as to try first with an EM algorithm, and this is very simple computationally, shapes the object in early iteration normally. Of course, it has some problems with the starting point and with stopping in the local minimum, but the first idea was, is it possible to deduce a kind of penalized AM algorithm in this situation? And yes, the answer was yes. So you have in this case, you start as usual for the AM algorithm with complete data and with penalized log likelihood for the complete data here. And then you have the latent variable Zj that are this one of G representation, and they have this probability that corresponds to the mixture weights, and they are actually what you are looking for, these PJs, but the values of Zj are unknown. Usually in the expectation step you are taking, instead of the log likelihood of the for the complete data, the expected value of this log likelihood with respect to the a posteriori distribution of Zj given Yj. And the formulas does not, I mean the formula for this function does not change so much with respect to the normal EM algorithm, only you add your penalization term. And also regarding this kind of a posteriori probabilities of Yj's coming from the component J, it stays the same. You use usually this information after the convergence of the EM algorithm to make the classification. So the largest, the component with the largest estimated posterior probability is the one to which the data point belongs to. And in the end, you Pj is also the same, only sigma j can be directly computed, and this is due to the very nice chain rule for the Kronecker product. And so we have a closed form also for the derivative with respect to Cj, and for the updates for Cj, and also for omega j. And in the case of Yj, we get also a nice interpretation of the soft thresholding. We can see here that it can be written with the help of the usual update for the EM algorithm, and this is kind of indicator function, and for lambda larger than special value here, so a weighted value of the usual update for Yj, we see that the component of Yj is put to 0. So it's a nice. Okay, so of course we started this not so long ago, and there is still a lot to do about it. And from a mathematical point of view, at least, I would really like to know if there is any clustering, model-based clustering algorithm with sensor data, because I actually didn't talk about this in here, but all our information there is actually censored, right censored. We do not let people or rats to actually find the treasure. They have maximum 60 seconds to do this, and so usually this is not taken in consideration. So I would really like to if there is nothing like this, I think this would be a very nice direction to research. Okay, thank you.
I was actually wondering whether you could like briefly comment the boundiness constraints in your theorem. In the theorem that you showed,
Yeah.
you had boundiness constraints.
Yes.
And I'm not sure that I understand what interpretation?
Yes, so it would be like if you think about the univariate case, it would usually you try to go away from this border of the, I mean, from small values of the variance. So I think this would be the generalization for variance. I mean, if there were, for example, first boundness on the eigenvalues of the inverse of the covariance, it's exactly this. So actually, you have low bounds for the eigenvalues, and then in the other case you have upper bound. So actually, you are restraining this kind of eigenvalues in this way. So I think this would be the interpretation.
Other questions?